All right, so this is lecture 16. This is the first part of it, the A portion of it. And basically what we're going to do today, right now, is we are going to introduce you to the energy equation. What we're going to do today is we're going to talk about understanding the energy equation, and then really want to talk about this alpha, which, of course, the font here kind of makes that look like an A. It's actually an alpha, so it actually kind of looks like that. You know, it's the Greek letter alpha. Okay, and then we're gonna apply it to solve a problem or two. And so what we want to talk about here is the energy into a control volume. And really, so we want to think about energy. And generally speaking, in this case, energy basically is head. Okay, so energy, I'm not going to do a full derivation because I don't really see the value in it. It gets into a lot of work terms and a lot of other terms that, I don't know. It's more thermodynamics than fluids, but really we're gonna think of energy as head, as head. Okay, so basically, like if I have some sort of control volume, and who knows what the shape of that control volume might be. It could be any sort of control volume whatsoever. I could have energy coming in. In this case, of course, this is a fluid class, so I'm talking about energy or head, okay, or head coming in. Okay, and I've also got, head leaving the system. Okay, this is the head leaving the system. Okay, and now that's fine and good. So in a balanced system with no inputs or outputs of energy, then what goes in is going to equal what leaves. So normally we might say, well, okay, well that means in equals out plus accumulation of energy. Accumulation. Okay, so now, unfortunately, or fortunately, depending on how you want to look at it, this is a really cool time in this course and in your engineering education, because this is probably the first time we're really going to start to deal with energy and all of its realities. Okay, there's not, we're not going to be dealing with frictionless pumps anymore. I mean, we will a little bit, but we're finally learning how to deal with the fact that there is friction in the system. So basically, one of the things that we want to consider as this fluid and this energy and this head moves into the system and then out of the system. Well, first let's label what's coming in. So we've kind of got some head coming in. So the head is going to look like this: P1 on gamma plus, Z plus Z. Let's make that an N. Plus, and this is not quite head. It's got this little alpha here, which we're going to talk about in a second. V1 squared on 2G. Okay, so that's kind of what's coming in to our system. And then we're going to have what's leaving the system, which is going to look like, this is an N. This is P out on gamma plus Z out plus alpha V out squared on 2G. Okay, so cool. So that's what's coming in, that's what's head that's coming in, head that's coming out. But what I want you to think about is in terms of, we want to start thinking about, well, what happens to, for example, if as this thing moves through the system, there's a friction on the walls. Okay, so I'm just going to kind of draw that as like red, as if it's friction in there, right? So that is a loss of energy. So we could think of that as something that is leaving the system. So that's kind of like an out. Okay, and we're going to call this thing head loss. Okay, so that is the loss of energy. Okay, so typically the way we deal with the head loss is we think of that as a loss of energy. So I'm just going to put it over here, and I'm going to call it HL. Okay, H capital L. Okay, so basically we've got energy coming in, energy leaving, energy lost. Okay, now there's still one more way that we can get energy into or out of the system, and that is, let's suppose somewhere between where it goes into our control volume when I leave, what happens if I have a pump? So if I do work on this thing with a pump, okay, so this is going to be the head added from a pump, okay? And so that's kind of what's more energy it's not coming in, but it's being added, HP. Okay, furthermore, I can have head lost to a turbine. Okay, and so what a turbine is you can think of it as the opposite of a pump. Okay, the water goes through this thing, it spins the turbine, and we use that to get energy. But in the meantime, the fluid loses energy. Okay, so we're going to say plus HT. Okay, and this is the energy equation, and it is, in undergrad fluids, the most powerful equation in undergraduate fluids. Okay, and mine's a little bit color-coded, but that is what we're dealing with. Okay, and so basically this head loss is due to friction, this head gain is due to a pump, and this head loss is due to a turbine. Okay, so that's really the equation, and I didn't want to really delve into the derivation. However, there's something interesting here, and I want to look at the velocity head. So the velocity head looks like this. Okay. Now what we're used to is v squared onto g from Bernoulli. Okay, but here, this is from energy. Okay, and now the question is, why the difference? Okay, first of all, let's talk about what this bar means. Okay, that bar means average. Okay, and this alpha, it has a name probably, but I can't remember what it is. It's a correction factor, so I'm just going to call it the correction factor. And the difference comes from this, okay? So for Bernoulli, Bernoulli works on a streamline. So if I have a streamline, okay, and I've got a 0.1 here, and I've got a 0.2 here, okay, well, there's only one V that applies. So like I could just take V1 and I could put it right there, and I could take V2, okay, and I could put it right there, and then boom, I'm all done. For the energy equation, that doesn't really work that way. So typically in an energy equation, we might have a control volume. So let's imagine we've got, I don't know, like a hose or something here, and we've got a hose here, and then we've got fluid here. And then what I have to do is I have to define the control volume. So here's my, let's define it in a different color. Here's my control volume. Okay, and here's where it's coming in right here. Okay, so this is in, and this is out. Okay, but note that what's coming in usually is going to have some sort of profile like this. Okay, and then when it's leaving, it similarly will have a velocity profile where it's not all going the same velocity. Okay, so in order to get the energy from this, you would normally have to integrate. You would normally have to integrate, in this case, dz, I guess, if that's a rectangular thing. But normally you'd have to integrate, okay, in order to get energy. Okay, basically you're going to have to integrate to make that happen. Okay, and we don't want to integrate that. Okay, so what somebody did is they said, well, they did this enough times and they did the math, and they said what alpha does is it makes it so there's no need to integrate. So what they noticed is they said, so alpha helps us handle the fact that the flow is not uniform. One day I'll do the full derivation as a video. So basically, alpha is defined as, the integral over the area of velocity cubed dA divided by the average velocity cubed times the area. Okay, and we'd have to get into the derivation as to why that works. I'm not concerned that you know that. Okay, the nice thing about this is that alpha is fairly easy to deal with. Okay, so basically as long as you just make sure that you're using this average velocity right here, and then what you're going to do is you're going to say, okay, well, what is alpha? Well, alpha equals 2.0 for laminar flow, in a pipe, and alpha equals 1.05, which is approximately, which we just usually take to be 1.0 for turbulent flow. In a pipe. Okay, so that's really what we're going to do here. You're going to check to see if something is laminar or turbulent, then you're going to decide that it's either 2.0 or 1.0 based on that. Okay, and the reason this works is because for laminar flow in a pipe, okay, we might end up with a cross section that looks like that. Okay, and so what is our V bar? Okay, V bar in that case looks like it's about like right there. Okay, V bar. Okay, and you can compare that to, say, like the center line right here to V max. Okay, and it's roughly a half. Okay, on the other hand, in turbulent flow, okay, basically because it's better mixed, okay, the V bar might be like right there, and it's almost the exact same thing as the V max. Okay, I guess it's about 1 over 1.05 of the V max. Okay, so that's kind of how this works out. Okay, so the last thing that's going to come into all of this equation here is, that's how we deal with the alpha, is what about these pumps? Okay, so I've got this head pump and I've got head of a turbine. Okay, so power is something we now have to start dealing with. Okay, and in this class, and some classes for power you use a capital P. In this class, we're going to use a W dot. Okay, so the rate of work. Okay, and basically W dot for a pump equals gamma times the head of the pump times the flow rate. Okay, so what I want you to do, think of it, this is the power supplied, let's zoom in over here, by pump to the fluid. Okay, so now typically we supply power to the pump. Okay, like usually you do this by plugging it into the wall or something. So there is a W dot, I don't really know what to call this. I'm going to call this W dot to the pump. Okay, so this is how much power I need to supply to the pump to make it work. Okay, now I want you to think thermodynamically. Okay, so if the pump is going to supply, say, 100 kilowatts to the fluid, how much do I need to supply to the pump? More or less than 100? Okay, if you're thinking thermodynamically, it's going to be slightly more. Okay, because I'm going to lose some energy because the pump is not 100% efficient. So basically what we're going to do is we're going to divide that by eta. Okay, where eta is the efficiency of the pump. Okay, eta is the efficiency. Okay, and it is expressed as a decimal, so like if it's 85% efficient, you'll put in a 0.85 right there. Okay, so this is power supplied by user to the pump. Okay, now notice this number is going to be a little bit larger than what the pump supplies to the fluid. Okay, I mean it's almost the exact same number, right? Except it's raised by a little bit. Okay, so I could redraw this as W dot pump on top. Okay, all right. So similarly, okay, that's for the turbine. I mean for the pump. Now we have to think about the turbine. Okay, so the W dot turbine. Okay, so the power of the turbine supplies equals gamma H turbine Q. Okay, so this is the power removed from the fluid by the turbine. Okay, now this leaves something open for possibility, and so I call this the power, I'm going to call this, I guess, from turbine. Okay, sometimes to me I know you want a quicker thing to write right there. It's better to write these things out so you know what you're talking about. Okay, so in this case, it's better to write it out a little bit so you don't get confused. So in this case, we've got this power coming from the turbine, and in this case, so let's suppose like up here, I remove 100 kilowatts of power from the fluid. I mean, of energy, or excuse me, 100 kilowatts of power. Okay, so every second we're removing 100 joules, 100 kilojoules. In that case, that's what's being removed from the fluid. If I'm the user, okay, the power user receives from the turbine, is that going to be larger or smaller than the power that the fluid loses? Okay, hopefully you recognize the fact that this is going to be slightly less. Okay, so if I multiply by 8, in this case 85%, okay, the turbine's not 100% efficient, so if I remove 100, I'm not going to get that full 100. I'm only going to get 85, okay, if it's 85% efficient. Okay, again, we could note that we could rewrite this as this part right here could be W dot turbine. Okay, so I could say W turbine times eta. Okay, and that's pretty commonly how you'll do it, just because a lot of times you will have already solved for this. Okay, so that said, we are 15 minutes in. Let's do the first problem. And let's go over here, and I'll pause it while I write out the example. All right, so here we go. So here's an example problem. So I'm given, there's head loss in this pipe here, and they tell us how much it is. Now notice the head loss depends on V squared on 2G. So which V squared on 2G do we want? It seems like we're going to want the V squared inside the pipe. Okay. Now in some ways this should make sense to you that the head loss in the pipe should depend on the velocity, because obviously if or maybe not obviously, but if the fluid in the pipe is not moving, it's not going to lose any energy to friction because it's not moving. Okay, it's just not going to move, right? So the faster it's moving, the more energy it will lose to friction. Okay, we've got a flow rate here of Q. One thing that's interesting, and I left the problem like this even though it's a little bit wonky, is that this thing does not tell you which way the flow is going. Okay, and that matters with the energy equation. It does not matter in Bernoulli because there's no energy lost. As soon as we start thinking in terms of the energy equation, okay, I did not mean to write that in red. As soon as we start thinking in terms of the energy equation, then it matters which number is your 1 and which one is your 2. Okay, so what we're going to do is we're going to assume in this case that Q could be going either to the left or to the right. But I'm just going to go ahead and pretend that it told you that the flow was going this way. Okay, that the pump was pushing things up. Okay, because the pump can overcome whatever it wants to overcome, at least theoretically. So what we're going to do is we're going to draw our control volume right here. Okay, and we're going to go like this. Okay, I'm going to stop dotting the lines because that was just taking too long. Okay, despite all of its loveliness. Okay, so now we're thinking in terms of energy. Okay, so what I need is I need an N. So I'm gonna call this my energy N, right here. Okay, where's the water leaving? Well, it's leaving right here. So this is my out. Okay, and I like picking those points for lots of reasons that you can remember from when we did the Bernoulli equation. So for example, this out is very nice because we have atmospheric pressure, we know the elevation. This in is nice because we know the elevation. And, well, that's really it. Excuse me. So what I want to do is I want to remind us what our tools are. All right, and let's see. So these are our tools, okay? But what's going to happen from now on is we're no longer ever going to use Bernoulli. Okay, we are now only going to use the energy equation. In many ways, I think of the energy equation as an improved version of the Bernoulli equation. Okay, so we are never going to use Bernoulli again. We're only going to use energy. Okay. The other thing we want to do is we want to stare at this. We want to recognize that there is no manometer, so we don't need to think about trying to use that to close our system. Okay. This is not asking for anything to do with forces on a moving fluid, so we're not going to end up using momentum. Okay, so in this case, we just have these three equations. Okay, I mean, ultimately there'll be a last equation because we want power supplied by pump to produce this Q, which means power pump is, we're going to use this equation right here. Okay, W dot of a pump. Okay, so we are going to need like one more equation, but for the fluids, for the basic fluids concepts, we're going to use energy equation, geometry, and continuity. So let's start with, I'm going to leave this space over here for my asides. Okay, and then I'm going to go ahead and write out the energy equation right here. Alpha V in squared onto G plus HP equals P out on gamma plus Z out plus alpha V bar out squared on 2G plus HL plus HP. Okay, not HP, HT. Let me go ahead. I think I usually do those in the opposite order. I don't think it really matters. HT plus H. I know it doesn't matter, but anyway. All right, so the first thing we're going to do is we're going to start simplifying this because some of these things simply don't exist. Okay, you'll note also that for now I'm using P ins and P outs. A lot of times it's more common to just use 1 and 2, although it is more correct to use ins and outs for the Bernoulli equation. I mean for the energy equation. So what we're going to do is we're just going to kind of walk through this. Okay, so the first thing we'll do is P in. Okay, notice in is inside of a pipe. How do I know? Because it's drawn with that little lip right there. So this means that let's see. So that means that the P in over gamma, it exists. Oh, by the way, this is water. We have to know what this is. All right, we can't just, I mean, we could solve it without that, but that would be annoying is what it would be. Okay, so that's going to remain where it is. Okay, the Zn, what's the elevation of the Zn? Okay, well, that is going to be our datum. Okay, so that's going to be 0. Okay, which means Z out is going to be 20 meters. Okay, because it's 20 meters higher than the datum. Okay, some of you might prefer to just make the Zn 20 and the Z out the Zn 20 and the Z out 40. Totally fine. Okay. I forgot here. I forgot the P out. What's the P out? Well, it's connected to the atmosphere. So we're going to make that 0 gauge. Okay. Now, what is the V in? Well, we don't know what the V in is yet, so we can't do that velocity in. What about the V out? Okay, so this one we've done. We don't know that one. What about the V out? Well, in this case, we're going to use what I like to call the Tahoe or the tank assumption. Basically, it's large. Okay, so this is the tank. So we use the tank assumption. If you don't remember that, go look at the Bernoulli video. Okay, now we've got an HP, which we don't know. There isn't a turbine in the problem, so we'll get rid of that turbine. And then we know the head loss is defined right here, so we'll go ahead and plug that in. Okay, so what are we left with? So we're left with P in over gamma, in this case gamma water, plus alpha V in squared onto G plus HP equals 20 meters plus HL. Okay. So basically what's going on here, and this is how I like to think about it, is that you've got a certain amount of pressure, and you know pressure energy. You've got a certain amount of velocity energy, and you've got a pump. And those are serving to raise the water 20 meters after overcoming whatever the head loss is. Okay, which in this case, let's go ahead and write that as 7v squared on 2g. Okay, and for that v, I'm going to put a little p on it, okay, because that's the velocity in the pipe. Okay, which I will note in this case, okay, I'm going to go ahead and erase the word in, and I'm going to write a vp there because that is the velocity of the pipe. The velocity in is the velocity of the pipe. Okay, so now we're getting really close actually. The only thing we need here is, how do we get at that? Okay, I stand corrected. I was just staring at this, wondering how we get at the pressure at in, and I realized I drew the problem incorrectly. So let's redraw this problem. I know this is a little bit annoying, but it looks like the problem was supposed to be like this. So this end's supposed to be open to the atmosphere. Okay, so it's pulling water in from somewhere off to the left. So if that is the case, then what that means is that P in over gamma, well, that is atmospheric. Okay, so it's going to be 0 gauge. Okay, so this is going to go away. Okay, so that's kind of annoying that I didn't pick up on that earlier, but I didn't. Okay, so we're just going to, I apologize for that mistake. All right, so now what we can do is I can say, well, HP equals 20 meters plus 7 minus alpha. Looks like VP squared on 2G. VP squared on 2G. Okay, normally you wouldn't arrange these like this, but I'm just doing this anyway. All right, so we need alpha and we need VP. Okay, how do we get VP? Okay, well, let's look up over here to our sides. We've already used the geometry, really, that 20 and that 40. So the continuity is what we're going to use. Okay, so we know Q. Q equals VP area of the pipe. Okay, so that's going to be 7.85. Don't be, what is CMS? Okay, a lot of people get this wrong on my tests, and it's always very frustrating. They see CMS and they think centimeters per second. Well, this is a Q. Is Q measured in centimeters per second? No, it's measured in cubic meters or volume per time. Okay, equals, okay, the velocity of the pipe, which we're looking for, the area of the pipe. The area of the pipe, oh man, okay, that's supposed to be given. Okay, D equals, or phi equals 1 meter. Okay, that's supposed to be given. Okay, so this will be pi times 1 meter squared over 4. So that's pi over 4. Okay, so VP in this case equals, oh, look how pretty that is, 10 meters per second. Seems a little contrived. Okay, probably never going to get those numbers in the real world. Okay, so we can go back over here and we can solve this sucker. Okay, now what about that alpha? How do we deal with alpha? Oh, we can't quite solve for that yet, can we? We didn't know what alpha is. Okay, so to do that, we need to know the Reynolds number. Okay, so the Reynolds number is VD on nu. Okay, so the velocity is 10 meters per second. The diameter is 1 meter. And nu, okay, in this system is approximately 10 to the minus fifth meters squared per second. Excuse me, 10 to the minus 6. Okay, now what's going to happen to you is that you're going to sit here and you're going to beat yourself up about this number right here. You're going to be like, I just went to a chart and the chart has temperature, and Dr. Wagner, you didn't give us temperature. Okay, so if I don't give you a temperature, assume 20 degrees C or 50 degrees F. But really in this case, you're going to see that it doesn't matter. So when we calculate this Reynolds number, we're going to get 10 divided by 10 to the minus 6, so we're going to get an answer of 10 to the fifth. Okay, notice it has no units, okay, because that's what it's supposed to not have. Okay, so once we get this Reynolds number of 10 to the fifth, notice that the transition to turbulent flow in a pipe, okay, so the Reynolds number is greater than or equal to about 4,000. Okay, so that's 4 times 10 to the third. Okay, so we are almost 2 full orders of magnitude larger. Okay, so whether or not I look this up and get to use a different temperature, like let's suppose I use, I don't know, this 100 degrees, right? I could get 0.294 times 10 to the minus 6. Okay, I could use a different value if I used 100 degrees C here. Okay, obviously that's drastically different water temperature, and it becomes less viscous. But notice that it's not going to have any effect on whether or not this is turbulent or not. Okay, it's not even going to matter, right? This number is a third the size of that one, so my Reynolds number would be 3 times higher. It doesn't matter. Okay, so usually it's not even close. Not even close. Okay, so you can see, so we're going to make this turbulent. Usually it's going to be turbulent, right? I'm going to have to, basically in order, because this viscosity is so small, okay, I'm going to have to doctor a problem to make it be laminar. So I'm going to have to like try to think of like, this is flow in honey. I'm going to have to make this number really small or make it flow really, really, really slow in order to make it so that you have a laminar problem. In truth, like if you're stuck for time, just assume turbulent and move on, okay? Because that's going to be your best bet, okay? So because of that, alpha equals 1.05, but we're going to assume it equals to 1.0. Okay, so let's go over here and solve this sucker. Okay, so we end up with HP equals 20 meters plus 7 minus 1.0 VP, which is 10 meters squared over 2, and the gravity in this case is 9.81 meters per second squared. Okay, so HP equals 50.581 meters. Okay, so basically what this means is if there were no friction in this system, well, actually I guess even if there were friction, the HP could raise the fluid the pump could raise the fluid 50.581 feet if there's no friction. Okay, if the fluid is absolutely static, such that it's pushing back on the pump, then and there's no movement, then this is how high it could like maintain a lake above it, okay, where there was no movement. Okay, normally, however, in this case, this is enough pressure from the pump in order to maintain this flow rate flowing against, the flow rate of 7.85 centimeters per second, cubic meters per second, with this head loss in the pipe. Okay, and raising it 20 meters. Okay, so now the last thing we wanted to know is the question is find the power supplied by the pump to the water. Okay, so the power supplied by the pump, that has an equation, W dot equals gamma HPQ. So this is, fairly straightforward. So the gamma, this is water, 62.4 PCF. Okay, remember, don't forget to put an S in front of that in case you're ever dealing with a different fluid. HP is 50.581 meters, and the Q is 7.85 cubic meters per second. Okay. Now, we can go ahead and put the numeric value here. Okay, so there's the numeric value. Ooh, what did I do? I made a mistake, didn't I? Did you catch it? What's my mistake? Okay, well, it's a units problem, right? I shouldn't have done this. All right, this is not 62.4. 62.4 would be if we were using the other unit system. Okay, I was just checking that, which is what you should do. Okay, so this should be 9810 newtons per meter cubed. Okay, so that's going to give us a totally different number. All right, so we get this different number. Okay, now notice I want to start thinking about units here. So meters cubed are going to cancel with meters cubed. So now I've got a newton times a meter. That's a joule over seconds. So I've got a joule per second. So those are watts. Okay. Now note I only used 5 significant digits. 1, 2, 3, 4, 5, because nobody wants to know more than that. And basically what I'm going to do is I'm going to make this megawatts because I don't want to write all that. And I'm only going to report 3. So 3.90 megawatts. Okay. Okay, which sounds like it is a big number. But, it is what it is. All right, so we're 32 minutes in. So we'll stop there, and I'll work one more problem. And the other problem is going to have to do with pumps. All right, take it easy. Okay, bye.